In this paper, we propose WireFlie, a novel mechanism for autonomous transmission line inspection drones. Existing robotic solutions for power line inspection have evolved in three main approaches. Contact-based inspection offer thorough examination but require manual intervention. Non-contact drone-based methods provide rapid inspection but suffer from limited visibility for detailed inspection. Recent advancements in hybrid systems have achieved power line latching capabilities but are limited by their inability to navigate inline obstacles while maintaining wire contact. We propose a hybrid system to combine autonomous locking with a seamless inline obstacle navigation. Some typical transmission line components that act as obstacles involve Stockbridge dampers, dual space dampers, repair sleeves, and spiral dampers. Here is the overview of our proposal. The methodology comprises four key phases. First, launch and approach from ground level with an operator assistance. Second, autonomous while locking using RGBD sensor. Third, navigation through obstacles while performing contact-based inspection. And finally, transitions to flight mode whenever it encounters a pylon. We developed an underactuated closed-loop mechanism with a roller head as shown in the left, which is mounted on a drone as shown in the right. The mechanism operates in two phases to avoid collision and ensure geometrical constraint while locking and unlocking. During detaching sequence, in-place rotation of roller head assembly followed by full arm rotation and vice versa while locking. Additionally, we also propose a control architecture. It has two core modules, the locking module and the obstacle avoidance module. Both utilize the same RGBD camera that adjusts its orientation based on the module that is active. The demonstration of locking module is shown here. It uses YOLO V11 for wire detection and segmentation. Then, the hierarchical control sequence first performs yaw alignment. Once aligned parallel with the wire, it centers the wire in the camera frame through lateral alignment. And finally, performs depth control to a reference depth of 15 cm before engaging the grip. This experiment demonstrates the mechanism's self-alignment capability. To test locking robustness, we introduce intentional offsets during wire approach, ensuring the wire was off-center in the camera frame C. The experiments show the mechanism's self-centering design effectively guides the wire into the correct locking position. For inline obstacle avoidance demonstration, four different types of obstacles were installed on the representational transmission wire setup. The obstacle avoidance module uses YOLO V11 for obstacle detection and classification, triggering appropriate maneuvers at a 0.3 meter detection threshold. This experiment demonstrates dual arm rolling to navigate over sleeves and dampers. For dual space dampers, the system detects the obstacle 30 cm ahead and determines which arm to open based on the damper's centroid position in the image. Here, since the centroid appears in the right half of the frame, the right arm opens while the left arm still maintains wire contact. To assess WireFlie stability during wind while locked to power lines, we simulated wind effects using 3 industrial fans generating wind at 8 meters per second. We tested 4 operational phases in rolling mode as shown. Maximum angular deviations are as follows: 4 degrees during stationary and rolling, 5 degrees during obstacle traverser, 8.2 degrees during opening or closing one arm. In this demonstration, the detaching sequence transitions to flight mode and gives control back to operator. Here, the operator lands the drone after getting control. The system's rolling capability was tested across different wire inclination angles alpha. The system successfully maintained positive motion up to an inclination of 20 degrees. However, for higher angles, a decrease in measured velocity was observed due to the increased slippage between the rollers and the wire. This limitation can be addressed by optimizing the system's mass, geometry, and friction coefficient.